Hello everyone, welcome back. This is our lecture for chapter 5. It's on hypothesis testing. This chapter is where we really extend what we've been talking about to not only understand our sample, but to then be able to understand the population as a whole that we're trying to study. So there's really two types of research questions when it comes to stats. One is, do groups significantly differ on one or more characteristics? These are going to be done using t-tests, ANOVA, chi-square tests. This is just asking, do these groups differ on something? Maybe it's some outcome or some attribute of those students or those individuals. So do groups significantly differ? The other one is whether or not there's a significant relationship among a set of variables. These are more asking the question, if this one goes up, does the other one tend to go up? If I increase my exercise, does that tend to increase my health? These are normally going to be done using correlation and regression. What you'll find out at the end is regression is kind of a blanket term that does all of this stuff basically, except for chi-square tests. But it's really good for you to understand when you're thinking about a research question, these are your two core categories on how to decide what your research question is. Now, the whole reason why we're going into hypothesis testing is we want to be able to use what are called inferential statistics. The reason why descriptive statistics, all the stuff we've talked about so far, they're limited. They rely only on raw data. They generally describe one variable only, maybe a couple. They don't address accuracy of estimators. They don't talk about the population. They're only talking about the sample. The question also is, how precise is the sample mean, or does it differ from a given value? We can't answer that with descriptive statistics. And last, we can't ask if there's a between or within group differences or associations happening. This really limits what we're able to talk about in terms of the data that we have. When it comes to inferential statistics, we want to be able to test a hypothesis. We're going to frame it around very specific versions of hypotheses that will help us understand what our data are telling us. And we're going to be using p-values for that. We're also going to be talking about parameter estimation using confidence intervals, where we're going to try to estimate how big an effect is or how strong a relationship is. One of the issues that we run into with inferential statistics is that our sample is not perfect. The estimators will vary from sample to sample. So when we take a sample, we know that our estimates are at least somewhat specific to our sample and won't perfectly represent the population. What that's called is sampling or random error, and it's variability that's just due to chance. If we're taking a random sample, we just may happen to get more of higher individuals in one category than another. And so just due to chance, our sample isn't going to perfectly represent the population. When it comes to inferential statistics, one of our goals is usually to try to get at causality. We want to be able to say this causes this other thing. This influences this. This reduces this. Now, causality depends on evidence from various fields and statistics. So every time we're talking in stats, we're going to be talking about evidence. We're not going to be able to prove anything with statistics, but we can provide evidence. Now, one example of this is with cigarettes. For a long time, the cigarette companies were fighting the developing evidence that was showing that smoking was causing serious problems in the lungs. But they kept using this idea against the researchers. They kept saying you can't prove it. And it was true because it would be unethical given the health outcomes and the addictiveness of smoking to actually assign a group to smoke and have another group not smoke and use an experimental design. That is our most solid way of showing causality. But even with that, it's only providing evidence. So what ended up happening is it took many, many studies over many years to show that this indeed was causing cancer and lung problems. When it comes to causality, we have a lot of things we have to work through. For one, we have to understand the credibility of our data, of our measures, and of our sample. This can be in any of our situations, and it can come from an educational, behavioral, biological perspective. We also need to look at the strength of association, ruling out the occurrence by chance alone. So we need to be able to say, this relationship is too strong or too big for us to really think that this is just due to chance. We also need consistency. We're going to talk in this class a little bit about reproducibility and replicability. What research needs to show is that research findings from independent research teams are showing similar, if not the same conclusions consistently. We also need temporality. In order for there to be a causal relationship, the cause has to come before the outcome. Another issue you have to think about, especially in experimental designs, is the dose-response relationship. Dose-response means at various dosages, there's going to be different levels of responses. And so if someone's just smoking one cigarette a year, they're probably not going to have an issue with their lungs. If someone's smoking a pack an hour, they probably will. And usually the dose-response relationship can be kind of complicated, where sometimes there's just no response up to a certain point, and then suddenly you can start to see that there is a response, something is happening. We also have issues of specificity and sensitivity of our measures and of our statistics. We get into that a lot more in the next class, the regression class. But it's the idea of, can you capture when something does happen and when something doesn't? And then another thing to consider is prevention. And there's a lot of ways that you can understand prevention, but here I want you to think about when you actually are using evidence to show a causal relationship. At some point, that information needs to be communicated in such a way that it's convincing to actually influence the public, to influence policy, to influence other researchers. So showing causality is a process, and it rarely can happen very quickly. Generally, it's going to take time. It's going to take careful thought and teamwork in order to start to show that. Ultimately, causality is often a judgmental evaluation of combined results from several studies. Consider another example of climate change. At very first, there was some evidence showing that things were happening. But there weren't very many people that were seeing its effects. It was mainly only researchers that really understand the field. But over time, there has been a lot of evidence building to show that climate change is happening and what it's doing. It doesn't mean that every study that came out was accurate. But combined, if you look at all these studies, it's becoming very clear that things are changing, and it has a strong relationship with certain things that are supposed to be the cause, including human activity. So how do we actually use statistical inference? Well, first, we need to go back to z-scores. So if you remember, when we were using z-scores, if it was with a normal distribution, even with individuals, we could look at it and say, okay, based on this person's z-score, let's say they scored a z-score of 3, we could say that they were much higher than the majority of people. And in fact, we could give an exact probability. We could say a score of 3 on a z-score or higher, the probability of that is really, really small. And if you remember the 68, 95, 99.7, higher than 3 standard deviations is like 1.5%. The issue is we're not very frequently interested in whether individual scores are unusual, but we're usually wondering how groups of cases or groups of people are unusual. And so when we talk about a p-value, we're talking about the probability generally that is about this group compared to some other group or some other standard. So we're really going to be looking a lot at the sample mean and looking at how that compares to some comparison. So when we're doing a hypothesis test, we're going to use this 6-step approach, and it's worth memorizing because we're going to be using it essentially the rest of the semester. First step is state the hypotheses, which is both a null and alternative. So we're going to make it very clear what those mean. The next step is select the statistical test and significance level. So we're going to decide what are we going to use to test this, and at what point are we drawing the line to say yes, it's significant or not. To do that, we're going to pick an alpha level, and we're also going to pick 1 or 2 tails. Generally, we're just going to go with 2 tails. In the homework, you'll have experience with both. But in practice, we're almost always going to use 2 tails. The next step is going to be select a random sample and collect the data. That is generally not as statistical oriented. So in this class, that's going to be a given that you collect a random sample and you collected the data. Step 4 is find the region of rejection. And this is going to be based on your chosen alpha and the number of tails. That's basically going to say if it's past this point, we're calling it significant. If it's not, then we're calling it not significant. 5th is calculate the test statistic. This is going to be a z, a t, an f, a chi-square. These are going to be things that generally we don't interpret directly, but give us information in order to make a decision on significance. And then our last step is write the conclusion. And we're going to write our statistical decision in context of our research question. So we're going to go through each of these and make sure it's clear. But I want you to understand that each of these steps are very well laid out, and they're not things that you just have to make up. In the end, when we get a test statistic, the test statistic is going to provide us with a p-value. The z is from a normal distribution, a t is from a t distribution, f from an f distribution, and chi-square from a chi-square distribution, but all of them are going to give us a p-value based on a distribution, just like what we've done with z-scores. So the p-value is the probability of observing a test statistic as extreme or more extreme if the null hypothesis is true. I want to take a second and help you understand what the p-value is actually telling us. Ultimately, for the hypothesis test, it's the core thing that we want to get out. So it's really helpful if you understand what it means. Best way that I've seen to understand it is think about going to a place, a universe, where the null hypothesis is true. We're going to talk about what the null means, but generally, almost always, it means there's no relationship or there's no effect. So even if in our world, in real life, there is an effect, we're going to go to a place where there is not an effect, where it doesn't exist. From there, we're going to understand that even in a world where an effect doesn't exist, just due to sampling error, there's a chance that we could get results that look like an effect exists. And so there's actually going to be a distribution of possible outcomes that we could get in this null world. So there's no relationship in this world, and yet we're still going to get a distribution of possible scores or test statistics. Now the p-value is going to say, in that world, how crazy is the result from our study? So in that world, we're going to say, okay, this is a result we got. Let's say a z-score of 2.5. We're going to say, how crazy is that result in a world where the null is actually true? And in that world, we're going to find out the p-value. And that p-value is going to say, how crazy, or in other words, how extreme is that result? So in other words, it's a probability of observing a test statistic that extreme or more extreme in that null world. If this isn't making sense to you yet, I'm hoping with repeated practice, it'll start making sense. But there's a lot of false understanding of what a p-value is, and you'll hear a lot of them. And so in this class, we're going to do our very best to make it very clear what the p-value means. And we're going to repeat it multiple times throughout the class. But again, it's just saying if the null is actually true, there's no effect. How crazy is our result? Ultimately, what that's trying to tell us is if our result is super extreme compared to what we would expect in the null world, then maybe we aren't actually in the null world. Maybe there is actually an effect. And that is what it's trying to answer. So again, a p-value, it's just talking about the null world. But if it's really crazy, then our conclusion could be that, well, this would very, very, very rarely happen if we lived in the null world. So maybe that isn't the world we're living in. Maybe there really is an effect and the null is in fact not true. So we've talked about the null a couple times. We're always going to be comparing to the null hypothesis, and you're going to see this pattern over and over again. But the null is almost always that the population means are the same. So why are we talking about populations? Aren't we comparing samples? Well, hypotheses are always specified in terms of the population. And we're going to use mu, that symbol, this funky u, it's mu, for the population mean, not the x bar. Because what we're testing is the population. If we just want to test the sample, then it'd be easy. We'd just say, is our mean the same as this other mean? Or is it the same as this other group? Or is it the same as this value? And it wouldn't be inferential. We'd just be saying, well, our sample is different than that sample. But what we want to be able to say is this group, the population that they represent, are they different than this other group, the population they represent? And so our null hypothesis is generally going to be this form. Now the alternative, so it's either called the research or alternative hypothesis, is that the null hypothesis is not true. In other words, these aren't equal, or one is higher than the other. These are one-tailed approaches. This is two-tailed. We'll get some practice with this in a moment. One thing that's really important to remember in science is this idea of innocent until proven guilty. So if there is not enough statistical evidence to reject the null, to say the null, it's probably not true, then we can't say that the null is true, because that is not what we're testing. In the end, we either find out if there's evidence against the null or if there's not evidence against the null. So when there is no evidence against the null, it's not significant, then it's inconclusive. Maybe we need a larger sample, or we don't have good enough measures, or our experiment wasn't built correctly. But we can never say, well, there is just no effect out there. Maybe after repeated, really well done samples and studies, we could do that, but definitely not with one study. Now, one problem with this is because it's inconclusive, most null results are never written up. People find null results and they just see it as a failure and they move on. This is not good for a number of reasons, and we'll talk about these later in the class. But when we don't write up the null, that means it's a waste of scientific effort. And that has a lot of consequences that come with it. But the reason is understandable. It's because the results are inconclusive, not as fun to write about. So when we talk about rejecting the null hypothesis, the assumption that we have is the null hypothesis is true in the population. If the p-value is very small, and how small? Well, that's based on the alpha that we pick. So if the p-value is very small, then we have evidence against the null hypothesis. So the assumption is already that the null hypothesis is true. We're just looking for evidence that that's not the case. So if the p-value is very small, then we have evidence against the null hypothesis. In other words, it is unlikely we would have observed a sample that extreme just due to random chance if the null was actually true. It's possible, it's always possible, but it's unlikely. Now the criteria, generally what we're going to be doing is the p-value is less than alpha. But it gives you the same conclusion if you look at the test statistic compared to some critical value. Now the conclusion, regardless of using the p-value or the test statistic, is we either reject or fail to reject the null hypothesis. We never accept the alternative hypothesis. There's a lot of reasons for that, but we don't have enough evidence to say the alternative hypothesis is true. What we're doing is we have evidence to say we are rejecting the null or fail to reject. Now we've talked about one-tail or two. We've talked about a two-tailed test, which is this one, a one-tailed. Now, a one-tailed test, what we're saying is we know the direction of the results. So one-tailed test is saying we already know the direction of the results before we even collected the data. Sometimes this is possible, but almost always we're just going to use a two-tailed test. When it comes to the computational stuff like the mean and the test statistic, there's nothing different. The only thing that will change is the p-value will be different. So a two-tailed test is splitting up the alpha, whatever our alpha is, which generally is going to be 0.05, 5%, between the two tails. So we'll have 2.5% on this side and 2.5% on this side. And so what we're saying is if our result, our test statistic, is out here or out here, then we're going to reject the null hypothesis. For a one-tailed test, what we're saying is it's all on one side, so 0.05, all of it's here. So if the test statistic's up here, we reject the null. But if it's here, or even way down here, we're not going to reject the null. It's only if it's up here in that one tail. So we can pick either tail. So if we think it's going to be a positive result or negative, we can pick either one. But the one-tailed test is saying we already know the answer. Now, in our statistical software, basically all of them are going to assume a two-sided p-value. So when they report a p-value to you, it's going to be a two-sided version, not one-sided. But note what it means. So what if I got a result of 1.8? In a two-tailed test, that's not going to be significant. In a one-tailed, if we assumed it was this side, it is significant. So it does change where we draw the line. Now again, I always suggest a two-tailed test because that's what our software is going to do and it's the safest bet. But you're going to see in the homework and sometimes in practice, there's going to be some that look at a one-tailed test. Another reason why we use two-tailed instead of one is it's generally more conservative. The rejection region is distributed in both tails, like I talked about. The other reason is if we know the outcome, we already know it's going to be higher, then why do the study? It can look suspicious to reviewers, and it can make it look like we're just trying to find significant results no matter what. So generally, it's just best to go two-tailed and avoid any appearances of already knowing your data or appearances of I'm just trying to find something significant. Now, one thing to keep in mind, when we choose an alpha, we are choosing our type 1 error rate. So when we say 5% or 0.05, what we're saying is we are okay with 5% of the time being wrong with a false positive. In other words, we are okay with 5% of the time saying there is an effect when in fact there's not. We won't know if we're in one of those situations. Type 1 error is just a rate of error, but we won't know if we're in a type 1 error situation or not. So type 1 error is this false positive saying to a guy, you're pregnant, so it's a positive test when in fact it is negative. Type 2 error is the opposite. It's a false negative. This one is generally when we don't have enough statistical power, which we're going to talk about in this unit. It's usually because our sample is too small or the effect is really small. And so we're going to fail to reject the null. We're going to say there's no effect when there actually is. So when we choose an alpha, we're choosing our type 1 error. When we choose our sample size and our measures, we are in some way influencing our type 2 error. Now remember, whenever you make a conclusion, there's a chance that you can be wrong. There's nothing we can do to totally get rid of type 1 error or type 2 error. So in general, we have this default of alpha 0.05, but there's nothing magical about it for type 1 error. It just means apparently we're okay with 5% of the time being wrong. Now we can let it be larger, say like alpha equals 0.1, if we'd rather not miss any potential relationship and are okay with some false positives. We can also let it be smaller if false positives are costly and we want to be really strict. So you have situations where you move it, and that's fine. Generally, the best practice now is to use 0.05 or 0.1 or 0.01, but report the p-value so people can see exactly what it was. So using what we've talked about up to this point, let's apply that to what we call a one-sample z-test. What this does is it tests a representative sample to some pre-known value. So one of the assumptions is that the sample is actually random and it's representative. There's nothing you can do to fix a non-representative sample. It's just part of the assumptions that we're making. And you can't test it. You can't say, oh yeah, this looks like a random sample. The best you can do is look at different characteristics and try to understand, does this look like it represents our sample or our population? We're also assuming that the SD of the sample population is the same as the comparison population. This one's hard to check, and we can't statistically test it, so we can't test that assumption. Last one is the variables have a normal distribution. This is something we can test, but notably it's not as important if the sample is large because of the central limit theorem we talked about in the last unit. If the sample is far from normal and or really small sample size, we might want to transform the variables in some way, like a log transform, square root, stuff like that. The way that we can test this is by looking at plots like a histogram, box plot, and a QQ plot. QQ plots are our best bet, usually. We can look at skewness and kurtosis, if you remember the cutoff values, plus or minus 2. We can use the Shapiro-Wilks test, but I don't recommend it. It's used sometimes, but it's very sensitive to sample size, so it's not a very consistent test. And you also can use the Kolmogorov-Smirnov test with really large n, but again, generally when you have a large n, you don't have as much of an issue with normality anyway. All right, so when it comes to APA, and we're reporting the results of a one-sample z-test, which to be honest, you're probably not going to use very many one-sample z-tests in your life. We go over this one because it's the easiest one to start with. But generally, it is not one you're going to use a ton. But the idea is, especially like APA and how things are reported, it's going to be very similar across the board. So we want to state the alpha and the number of tails prior to any results. We want to report the exact p-values, usually 2 decimal places, except for when it's really small. Then we go to 3 and we say less than. For example, a one-sample z-test showed that the difference in the quiz scores between the current sample and the hypothesized value were statistically significant. That's a really good way of putting a situation. All right, so with all of that in mind, let's go through a full example of a one-sample z-test. So the situation here is after an earthquake hits their town, a random sample of townspeople yields the following anxiety scores. So we have this list of scores here. Now assume the general population has an anxiety scale that is expressed as a t-score so that mu is 50 and sigma, the standard deviation, is 10. If we go through our steps, the first is stating the null and alternative hypotheses. The null is that our population is equal to this other population of 50. The alternative is that they are not equal. Now, the next step is choose the test statistic, your alpha, and the number of tails. So we're going to use a z-stat with an alpha of 0.05 and 2 tails. The reason why we would use a z-stat is it's normally distributed, and we know the population, comparison, mean, and standard deviation. If we don't know one or either of these, then we're going to have to use a different test. So here we can use a z-test. So you can see what the distribution looks like. First thing that we want to do is calculate the standard error of the mean. And that is going to be right here. It's 10, your standard deviation, divided by the square root of your sample size, which here is 10. So what we have is 3.167. That's our standard error of the mean. So this is going to tell us about the distribution of sample means. So we're going to say, is this group of people right here, are they different as a whole than this comparison population? So we calculate our sample mean, and if you calculate it as 58, now we're going to say rejection region, we're going to put 0.05 in both tails so that each one has 0.025, which puts our critical Z at plus or minus 1.96. So we're saying we're drawing the line right here and right here. Anything on this side, we're going to reject the null. Anything on this side, we're going to reject the null. Anything inside, we're going to fail to reject. In other words, if we get a z-score from this that's bigger than 1.96 or more negative than negative 1.96, we're going to say there's a significant difference between our sample and the other. So let's calculate this. So the mean of the population is 50. We already calculated the standard error of the mean. That's 3.167. So we can calculate our z. It's our mean minus the comparison mean over the standard error. So 58 minus 50 divided by our standard error, we get 2.52, which means we are somewhere over here. Which means we reject the null hypothesis. So the z-stat falls in the rejection region, which is evidence that the population's mean is not 50. In other words, you could say after the earthquake, townspeople's anxiety levels are higher than 50 on average. It doesn't mean everyone is above 50. We have this person, they're pretty chill. This person's barely above 50. But as a group, on average, their anxiety levels are higher than 50. All right, a few cautions. Now that you've seen one example, statistical significance only says whether the effect observed is likely to be due to chance alone because of random sampling. So it's saying if we're in the null world, it's just saying how crazy is our result? And if it's really crazy in the null world, then maybe there's not a relation, or maybe there is a relationship and the null is not true. But the thing is it may not be practically important. That's because statistical significance doesn't tell you about the magnitude of the effect, only that there is likelihood that there is an effect. An effect that is significant could still be too small to be relevant. For example, you might be working in a clinic and you are looking at a new treatment, and it may be significantly better than the old treatment. But when you look at the effect size, it's not very big. In other words, there is a difference. Your treatment is a little bit better, but not very much. And that is important, especially when it comes to knowing, should we use this if it's more expensive because it doesn't really do a whole lot more? Those are things that you need to know. So with a large enough effect size or a large enough sample size, significance can be reached even for the tiniest effect. So if I have a sample size of 1 million, even a really, really small effect will still be significant. Now, another example, a drug to lower temperature is found to reproducibly lower patient temperatures by 0.4 degrees Celsius. But clinical benefits of temperature reduction only appear for a 1 unit decrease or larger. In other words, it is working. It does help patients lower their temperature, but it's not going to do anything to actually help the patient, because in order for it to actually really truly help them, it needs to be at least 1 degree decrease or more. So again, statistical significance does not mean practical significance. Another caution: don't ignore the lack of significance. Now, there's a sentence that I love to use, but it's confusing, but we'll think about it for a sec. So absence of evidence is not evidence of absence. Absence of evidence is not evidence of absence. In other words, having no proof of who committed a murder does not imply that the murder was not committed. When it comes to significance, we may not reject the null, which means we have an absence of evidence. We don't have evidence. But it is not evidence that the null is actually true. So just because we get a non-significant result, that is not evidence in favor of the null. That is just a lack of evidence against it. So we're going to go through a quick example in R. We're going to use a cancer data set again. Clean it up. Going to describe our sample. So we're looking at age and total CW4. We can test for normality with a Shapiro-Wilks. Again, I don't always recommend this, but it can be done in R, and here's the code for it. We can also check for normality with a histogram or a QQ plot. This one, you want the line to be along a nice straight line. It's fairly normal here. You can draw a fairly straight line through all of them. For this one, not so normal. A straight line, it doesn't really work. You have this kind of S shape happening. So it's a non-normal result for the total CW. And now you might be wondering, we didn't even run a one sample z-test. Well, it's partly because you're probably never going to actually use it in practice. We taught you about the z-test because it's going to help you understand other tests that you're actually going to use. The idea behind it is so closely related to other things that we've already done in the class that it's the easiest starting point. So from here on, we're going to start talking about tests that you're actually probably going to use. We're going to talk about things related to those tests, including statistical power. All of these things are totally necessary in order for you to understand how to interpret your results. So we're going to start with this. Hopefully this laid a good foundation for you to understand what hypothesis tests are and why we use them. If you have questions, please post it to the discussion board and we can discuss it in class. Our next topic is going to be confidence interval estimation, and we're going to introduce the t-distribution.